Training a massive neural network on trillions of tokens produces a base statistical engine optimized for next token prediction. This model excels at completion, but it lacks the internal instructions required to function as a responsive assistant. These base models contain an astonishing amount of latent knowledge, yet they lack structural constraints and conversational state awareness, which often leads them to repeat user questions rather than answering them. To transition from raw prediction to a reliable agent, engineers move the model into post-training, a rigorous phase that imposes logic and human alignment onto the statistical engine. We are going to examine the architectural blueprint of this process, building the complete post-training pipeline step by step. This construction involves data curation, supervised fine-tuning, preference alignment, model merging, and a methodology for scaling compute during inference. While pre-training builds the raw cognitive engine, post-training installs the steering wheel and pedals. The post-training pipeline requires a fraction of the data used in pre-training. We move from trillions of tokens to tens of thousands of high-fidelity examples, shifting the engineering bottleneck from volume to absolute quality. Data is filtered through three vectors: accuracy, verified by code solvers, and the diversity of the samples. Over-reliance on synthetic data generated by other models causes a collapse in embedding diversity. To maintain a broad range of capabilities, the dataset must include varied, human-sourced interaction patterns. This photo of the Eiffel Tower represents a typical low-complexity prompt. How tall is the Eiffel Tower? To train a useful assistant, we must evolve this into a high-complexity instruction, asking the model for a multi-step response that includes structural history and metric conversions. Once curated, these Q&A pairs are mapped into a rigid state machine structure, known as a chat template. Engineers inject specific system tokens into the text, labels like mstart, user, and assistant, to teach the model exactly where conversational boundaries exist. Without these strict templates and a diverse dataset, the model cannot distinguish between its own internal state and the user's input. To inject specific domain knowledge and formatting rules into the weights, we use supervised fine-tuning, or SFT. Retraining every parameter of a 70 billion parameter model is computationally expensive. It requires enough video RAM to store the frozen weights, active gradients, and optimizer states simultaneously. This shows the industry standard for reducing that load: low-rank adaptation, or LoRa. The process freezes the main network nodes and attaches two small active matrices. Only these are updated, reducing trainable parameters to 0.5%, drastically lowering hardware requirements. For single GPU environments, engineers use QLoRa, which compresses the frozen base weights into 4-bit precision to fit the model into consumer-grade memory. The training run requires efficient attention mechanisms, like flash attention, to process long context windows without memory overflows. By isolating updates to these auxiliary matrices, LoRa allows developers to specialize massive models without the need for data center scale compute. SFT teaches the model how to follow a format. Preference alignment is then used to teach the model which behaviors, such as tone and safety, are prioritized. This phase uses contrastive data pairs. For every prompt, the model sees a chosen response and a rejected response, learning to maximize the probability of the preferred behavior. This flowchart illustrates the hardware requirements for proximal policy optimization, or PPO. It requires 3 models loaded simultaneously. PPO tracks the KL divergence between the frozen and active models, a mathematical tether preventing the degradation of base capabilities. Modern pipelines frequently use direct preference optimization, or DPO. This algorithm bypasses the standalone reward model entirely, optimizing the active policy directly on the chosen and rejected data pairs. By removing the need for a third model in memory, DPO makes preference alignment far more stable for smaller engineering teams. We can also enhance models without further training through model merging, a technique for fusing different weight sets directly in parameter space. Fine-tuning a model on a narrow task, such as a specific language like Finnish, often results in the loss of general reasoning skills. By averaging the weights of a specialized Finnish model with a broad general-purpose model, we can retain the specific language skill while recovering the broader capabilities of the original. Complex merges use the ties mechanism, which prunes redundant weights and resolves conflicts between positive and negative parameters to create a unified consensus grid. Model merging allows for the modular stacking of distinct abilities, combining specialized layers into a single weight set at zero compute cost. Evaluation is the final bottleneck. Without precise measurement, it is impossible to determine if a training run actually improved the system. Automated benchmarks like MMLU are reproducible and fast, but multiple-choice questions do not capture the nuances of how users interact with a model in a chat interface. Human preference rankings, such as Chatbot Arena, provide a more realistic signal, but human raters are often biased toward longer or more confident answers, regardless of factual accuracy. Direct. This chart shows a distinct disconnect. Data points for automated benchmark scores on the x-axis show no statistical relationship to the human preference rankings on the y-axis. Most teams now utilize a hybrid approach, using large models as a judge to scale preference evaluation while maintaining a suite of targeted benchmarks for logic and math. To bypass the diminishing returns of scaling training data, developers are moving compute resources from the training phase to the inference phase. Standard use relies on zero-shot decoding, taking the first answer the model generates. Test time compute instead generates multiple diverse reasoning paths for a single problem. Systems can use majority voting to pick the most common answer from many samples, or best of n generation, where an auxiliary model scores each path to find the most accurate result. The most advanced implementation uses process reward models. Instead of scoring the final result, it evaluates the reasoning step by step, pruning logical errors in real time. By expanding only the valid steps, the model arrives at a verified conclusion. This methodology proves we can trade increased latency during inference for significant gains in logical reasoning. From data curation and SFT, through preference alignment, merging, and inference scaling, we have constructed the full post-training pipeline. This engineering loop is what transforms raw statistical capability into an aligned, capable assistant. To see these post-training techniques implemented in code, visit the Learn by Doing with Steven YouTube channel. For more in-depth discussions on the data engineering that fuels these models, subscribe to the Steven Data Talk podcast on YouTube Music, Spotify, or your favorite platform. Check the description for links.